Now we're going to discuss how charges are transferred. And there are several ways in which charges are transferred, and we're going to take a look at many of those different ways. The first is by conduction. And conduction, just like with heat, conduction is the transfer of charge through direct contact, where the charge is transferred from one to the other. And you can see in diagram 1 on the left that a neutral metal sphere rests upon an insulated platform. And then you bring in an aluminum plate in the middle diagram that's positively charged, and it comes in and touches the metal sphere. And when the metal sphere is touched, then the electrons are attracted by the positive charges of the aluminum plate and are drawn off the sphere from the sphere to the metal plate. Once the metal plate is removed, in diagram 3 on the right, you see that the negative charges have gone with the plate, decreasing its positive charge, but also leaving positive charges unaccompanied by negative charges on the sphere as well. So now both have some degree of positive charge. Now, the law of conservation of charges is very much the same as the law of conservation of energy or the law of conservation of mass, and that is the total charge that you start out with before and after an interaction has to be the same. So in diagram 2, you have the total charge just in the plate before it touches the ball or the sphere. And then you add the charge in diagram 3 on the right between the ball and the plate, and you get exactly the same number, and it will be the same charge. So for example, you have 6 pluses on the plate in diagram 3 and 5 pluses on the sphere. Then you should have 11 pluses on the plate in diagram 2, which I think if you count them, you'll see that there are 11 there. And what that says is that the total charge is conserved, and that's the law of conservation of charges. Grounding is a term that's used as the process of diverting unwanted electrical charge into the earth. And so it takes electrical charge and diverts it into the dirt or into the earth and prevents it from wreaking havoc in other places. Another way of transferring charge is called induction. Remember that first one was called conduction. This is called induction. Induction is the transfer of charge at a distance, that is, without direct contact. Induction results in two charges, the opposite charge closest to the original object, and a similar charge farther away from the original object. The result of induction, unlike conduction, is temporary. That is, as soon as you move the inducing agent away, then everything returns to the way it used to be. So here you have a charged rod, which is coming down from above, and it's approaching an electroscope, and it attracts positive charges and repels negative charges. So you've induced two charges. You've induced a positive charge on one end, close to the rod, and a negative charge on the opposite end, away from the charge. And this process actually is the way an electroscope works, that these negative charges repel each other and they separate, and it detects the charge that has occurred. We'll show you that in just a second. So this is induction. Current, as I've said in the past, is the flow of electrical charge from one point to another. In normal conditions, gases will not conduct electrical charge. For liquids to conduct electrical charge, there must be charged ions or electrolytes in the solution. So here we have A, which is distilled water, which does not contain any electrolytes. It will not conduct electricity, so the light doesn't come on. B is when you have something in the water, but it is not dissolved into ions, or it is not ionized. it does not conduct electrical charge. Therefore, the ions are fixed in place, so they can't conduct electrical charge, and again, the light doesn't come on. C is a situation where you have a liquid that has electrolytes floating around, positive and negative charged electrolytes, and these will move, and in the process of their motion, they will allow the motion of electrical charge to either the positive or negative electrode, and this results in the light coming on. Solids that have free electrons, that is metal solids particularly, those free electrons can conduct electricity, so they are good conductors of electricity as well. So here's an example of a metal that has free electrons floating around in there, and they will allow the motion of electrons through the metal molecules, even though the molecules themselves are not necessarily moving with the electrons. An electroscope is a simple device that's used to detect small electrical charges, and you can see that if the rod is charged, based on what we showed a couple of slides ago, it will cause those leaves to separate. Electroscopes can be a simple arrow which will point in the direction of an electrical field. On the left here is what's called a Van de Graaff generator, and it's a generator of static electricity. An electrostatic generator is a device that produces electrostatic charge, and it does that by rotating a belt that is charged on one side positively and charged on the other side negatively, and this motion of the belt through the globe causes the globe to become charged. The globe takes on a positive charge, and this little sidebar here is negatively charged. And this is exactly what you see on these Frankenstein movies or some of these other old scientific movies when they show the electricity arcing across from one globe to another. What they're showing you is a Van de Graaff generator generating electricity this way. You can generate huge electrical charges with such a generator. The most commonly used electrostatic generator is called a Van de Graaff generator, and as it says here, it can produce in excess of 5 million volts, which is a huge electrical charge and can cause a lot of trouble if not controlled well. The generated electronic charge always moves to the outside of the charged object. Okay, so if you have a object that's hollow in the middle, the charge will move out to the periphery of the charged object, which is why it's very safe to be inside a barn during an electrical storm. If the barn is struck by lightning or in some other way is compromised, the electrical charge will move out to the walls of the barn, and you on the inside will be very safe. So how does the lightning occur? Lightning occurs, it's a very interesting thing that happens with lightning. So let's go through this very briefly. First of all, a single stream or an initial stream of electrons comes from the cloud towards the ground. And that stream of electrons that you actually can see, is called a stepped ladder. And that stream of electrons causes the Earth to respond, and the Earth responds with positive charges called a positive streamer. And this is the positive charge on the ground that's attracted by the negative charged electrons that have come down from the stepped ladder. And then the third step is the return stroke, which is shown with the arrow here. And this is the upward current of positive charge from the ground to the stepped ladder. And if you watch a film of lightning striking, you'll see a downward, initial smaller downward, which is the stepped ladder, and then you'll see a second bolt which if you watch carefully looks like it's going up. Sometimes it's hard to see the direction of that second bolt, and basically that is the positive charge coming up from the ground. Now when people are struck by lightning, they're generally struck by the downward stepped ladder as opposed to the upward stroke. Now if you own a large building or you live in a place that has a lot of problems with electrical storms, you may see on the roof of some buildings something called a lightning rod. And a lightning rod is a device to protect buildings and other structures from being struck by lightning. And actually, they sometimes put lightning rods on small vehicles and things of this nature as well. And what a lightning rod does is it acts as a lightning gatherer, and basically it drives or allows the lightning a very easy path into the ground, so that it strikes the lightning rod, runs down a copper cable, which is a very good conductor of electricity, into the ground cable, into what's called a ground enhancement material, which is material that will allow the dissipation of the electrical charge. And this basically, lightning is going to occur, so the best thing to do is to try to control it in some manner. And this is the way that many people do it, is they put a rod on the roof with a electrically conducting material that leads it to the ground so that people are not at risk. Now obviously it's not a good idea to be holding on to this copper material when a lightning strike is coming around, because if it strikes that and you're holding on, you're liable to get electrocuted. So how do we store charge? You know, we talk about batteries, and we will talk about batteries in future lectures. The oldest device used to store electricity was called a Leyden jar. And a Leyden jar looks like this. And you attach your electrical source to this metal rod on top, and it causes the middle rod to be positively charged, because the negative charge goes in the top and draws all the negative up into there, and then the positive charge occurs in the middle. This is put into this tin foil, and then the outer part of the jar becomes charged negatively, and this will hold on to charge for a short period of time. Now the modern device for holding or storing electrical charge is called a capacitor. And a capacitor looks something like this. You have two parallel plates, one of which is positively charged, it's on the bottom. The other is negatively charged. These become charged when you feed electricity into the top, and it negatively charged, and then the material in between prevents the actual flow of electricity. And so what you have is the one plate becomes negatively charged, the other plate becomes positively charged. And when these discharge their electrical field is when they lose their charge. In the process of losing their charge, they give up their electrical charges, and that is how they work. Now these used to be tubes, and if you open an old radio, a very old radio or television, you'll find a bunch of tubes inside. And those are basically capacitors that hold on to electrical charge. And when people used to work on these, they would tap these tubes, and you could see the electricity arcing across the tube. And they would do that so that they wouldn't get electrocuted. Nowadays, the capacitors are all solid state, and they're not as much risk involved in working on them. So what are some practical uses for static electricity? One of the most common that you run into is a paper printer. Many of, not the inkjet, but the other kinds of printers use electrostatic charge to print. And what this does is that they charge the drum. As you can see, the drum is positively charged, and the light when light strikes this positive charge, it leaves a replica image. And then the toner, which is negative, is attracted to the positively charged paper that comes through, and at that point this causes the toner to stick to the paper at the points based on the image that was printed on it by the drum. And then this toner is then fused to the paper by another set of wheels. And that's called xerography, is writing with static electricity. Another way that static electricity is used is in air cleaners, and you pass air through a charging section. That is, the air in there is charged, and then it passes through electrically charged plates, and then the particulates, which are now charged, will stick to those plates. And then you wash the plates off and you've cleaned the air in the process. And then the third is in certain types of paint, when they paint cars, they will negatively charge the car and positively charge the paint gun, which positively charges the paint. And so that causes the paint to stick much more accurately to where you're spraying it. And they will use that to paint cars.